Hi everyone, Mr. Boltri here, bringing you a supplementary video to video 2.3, where we're going to talk about an advanced mathematical concept called the separation of variables. And this comes up really often in drag problems, like we saw in our last class. So today we're going to look at this just one separation of variables question from the packet that we looked at in class today. So we remember that there's an object falling and then there's a resistive force. Which gives an acceleration equals g minus bv, where v is the velocity and v is a constant. So if we look at cases like small and big times, which of the following is a possible expression for the speed of the object? So let's highlight some important words. We have the resistive force, and then we have the acceleration, which is given as this function. But before we dive deep into the math, and I should have said first, it's going to be a very math-heavy video, and I'm going to gloss over some topics that your math teachers will go a lot more in depth into. I'm going to spend 1 minute where your calculus teacher might spend an entire lesson. So if it feels crazy rushed, that's just because in physics, all I need you to know is the tricks of how to do things. And then your math teacher is going to help you to understand why it is the way that it is. But before we dive deep into the math, let's just try to, if we didn't want to figure all this out on the day of the exam, because we only have about 60 seconds for this question and the math is going to take really long, let's just try to think our way through it. So yes, this is going to be a very important expression for when we're doing the math, but if we were to think our way through it, let's think about very large and small values of t. So for very small values of t, like t equals 0, when the time is 0, the velocity needs to be 0 because the problem says it's released at rest. So if we're looking at these answer choices, does any of the velocity at time equals 0 not equal 0? And we can see that this is true of two of them, because e to the 0 is 1, so the velocity is going to be g over b. That's not 0, so that's not right. And then here the velocity equals some v naught that is specifically not equal to 0. So we can right off the bat eliminate two answer choices and give us a much better chance at just guessing the right answer. But we don't need to guess. We can also think about, well, if we think about velocities that are really big, like 1,000 or the time, as the time goes forward, the velocity, is it getting bigger and bigger and bigger? Well, we know because of drag force or resistive force, that as the velocity gets bigger, the acceleration gets smaller and approaches 0. So we could say that the limit as the time approaches infinity of the velocity is a constant. That we could call that terminal velocity or whatever. But the important thing here is that as the velocity gets bigger, as the velocity gets bigger, or as time goes on, we need the velocities to sort of level out to some constant value. The velocity can't just keep getting bigger and bigger and bigger and bigger and bigger. That just doesn't work with the acceleration function that we have. So there we can eliminate two of the other choices, and actually the correct answer here is A, because here the velocity as time goes on, the velocity just gets bigger, and here as time goes on, the velocity just gets bigger. So the correct answer choice is A, and you can do it in 1 minute as opposed to 10 minutes, which is how doing all the math is going to take us. So just kind of stop and think through the problem before you just dive into the math. But if this was an FRQ, then we might have to go through and do all of the nasty math, which is what I'm going to show you now. So back to the equation, A equals g minus bv. So given this equation, we might want to, and our goal is to find the velocity, we might want to integrate both sides because the integral of acceleration is velocity. So then if we are able to integrate this, then we're going to get the velocity function. So the integral of A is just velocity, and the integral of this is, with respect to time, is gt minus bvt. So boom, that's our answer. But unfortunately, we don't see that answer in any of the answer choices. And why is that? It's because we're not allowed to do this. And the reason is we can't integrate bv with respect to time because we don't know the function for velocity with respect to time. So this bvt, this works if v is a constant, but v is not a constant. It is a function that changes with respect to time. So we can't just throw the v in there. So this is not actually a correct function for the velocity with respect to time. So we're back to the drawing board. What are we going to do? And this is where the advanced mathematical concept of separation of variables comes in. So we know we can rewrite acceleration as dv dt equals g minus bv. And so what are we going to do with that? So we're going to rewrite this as so we have dv, and we have a function that changes with velocity over here. So we're going to rewrite it sort of a little bit like this. And you can think about this as kind of cross multiplying. We like took the dt and then multiplied it over here, and then we divided both sides by 1 over b minus v. And the reason you might wonder to yourself, well, how would you know to do that? And the reason I know to do that is because I would really like dv's to be with my velocities. So I get this function that has velocity in it over next to the dv, and then I'm just going to integrate this side with dt. And your math teachers would be really mad if I suggested that this was sort of cross multiplying, because it's not really. That's kind of not what we're doing. It's a little bit more complicated. We did move this to the other side so it could be next to the dv, and then we're really integrating with this. It's kind of like the chain rule of integration, where we're taking the dv, the derivative of velocity with respect to time, and then integrating that with respect to time. But when we clean that all up, it turns out to be it looks like the integral of this function with respect to velocity. And then on the right, we're taking the integral with respect to time. Because you can't just do one thing to the left and then one thing to the right. We have to do the same thing to both sides. So what we're really doing to both sides is taking the integral with respect to time. But then because of that nice little chain rule, it cleans up to just be, looks like the integral of dv. So the trick to knowing how to do this, this is kind of the big trick. That you kind of just, until your math teacher explains it, which isn't going to be for several months, you kind of just have to know that we want these to be next to the dv because this is a function that changes with respect to velocity. So we can't integrate it with respect to time, we have to integrate it with respect to velocity. Okay, so now that we have this beautiful nasty function, we can actually integrate it because we have the velocities with respect to, integrated with respect to velocity. But in order to actually be able to integrate this, I'm going to have to teach you a couple more tricks. So the first trick that I want to teach you is, and again, your math teacher will tell you exactly where this comes from and how you can derive it for yourself. But I just want you to memorize that the integral of 1 over x with respect to x is the natural log of the absolute value of x plus c. And you might notice that this is x to the negative 1, which is the only power that doesn't follow the power rule. It's kind of the special exception, and because it matches this function. Because if we tried to do the power rule for x to the 0, we would not get x to the negative 1 because x to the 0 is just a constant. We take a derivative of a constant, it's just going to be 0. So this is why this is sort of the special exception case here. So this is the one exception. And the other exception is basically called the chain rule for integration. So you know the chain rule for derivatives. This is the opposite. It's the chain rule for integration. So if we wanted to integrate the cosine of 3x dx, you might think that that is the sine of 3x plus c. Because if we take the derivative of this, we get the cosine of 3x. But don't forget the chain rule. If we take the derivative of the outside, keeping the inside the same, times the derivative of the inside. So it would actually be, if we took the derivative of this, it would actually give us 3 times the cosine of 3x. So we need to multiply by a 1/3 in order to give us the actual appropriate derivative. So this is the appropriate derivative. And this will be called U substitution when your math teacher talks about it. But it's just basically the opposite of the chain rule for integration. So you need to know both of these two tricks in order to do the actual integral. And oh my gosh, we are covering just so much stuff today. And it's okay if it doesn't make 100% sense right away, or it's okay if it doesn't make 100% sense for a couple months until you talk about it in your math class. But for right now, we're just trying to understand all the tricks to get to where we want to go. Okay, so we're going to have to do the natural log thing and then the chain rule U substitution thing. And then we get this is the derivative or the antiderivative of the function. And technically, I do need a plus c over here on the left side too. But since that's just any arbitrary number, I can just take that plus c and add it to this other side, and we're still left with just kind of a general plus c. I could call it 2c if I wanted to, but just because it's a made-up number that we don't know yet, it doesn't matter what value I use for it. It can just be plus c. So here, this is the natural log that comes from the 1 over something, and then this negative 1 over b is because it's the derivative of the inside business that I was talking about with the chain rule stuff. So this is the antiderivative, and this is very close to our answer. And from here on out, we're just going to be doing some algebra simplification to get the answer that it looked like in the multiple choice question. So from here, I can multiply both sides by negative b. And again, if I multiply c by negative b, since negative b is a constant and c is a number that I don't know yet, I can just leave it as c. So we get negative b times t plus c. And then over here, I have all my natural log stuff. So then to clean it up even further, I can do e to both of the sides. So e to the natural log of this just cleans up to be a g minus bv. And then over here, I get e to the negative vt plus c. Again, just cleaning up, cleaning up, cleaning up. If I remember my exponent rules, I can rewrite this as a g minus bv equals e to the negative vt times e to the c. That's just kind of one of the rules. And e to the c, again, c is just some random constant that we don't know yet. So e to the c, I can just rewrite as c. And we're getting really close now to the final answer. But it might be nice if I were to solve for c. And one way that it's easy for me to solve for c is to plug in t equals 0 and v equals 0. So at t equals 0, this is just 1, and v equals 0. So we can find that c actually equals g. And then we can move the g to the other side, divide by, or multiply by -1, and then divide both sides by b. Oh, shoot, I forgot to, then we could factor out a g, and then divide both sides by b, and we get the actual answer that was given in the problem. So, oh my gosh, that was so much, so fast. And if you want to watch the video again, that's fine. But if you kind of just want to soak in all of the advanced, crazy math that just happened, that's okay too, because you are not going to be expected to replicate this for quite a long time. If I'm trying to think about if ever the AP exam is going to would ask you to do something as complicated as this. But I just kind of wanted you to see it happening at least once. So then if you have to recognize it happening in a multiple choice question, then you would be sort of able to do that. And you'll notice that this is the same answer as option A, which we got a whole long time ago with a lot simpler method just by thinking about it. So you don't always have to dive right into doing the math. You can sometimes think your way through it. And it might be better just to sort of try to think your way through it, give your best answer, and not waste a good, oh my goodness, a good 10 minutes trying to do all the math for this problem. So that's kind of the mathematical trick of separation of variables, which comes up a lot with drag problems because of how the acceleration is getting smaller and smaller and smaller as the velocity and the time are getting bigger. So we are going to talk about this, I'm sure, more in our next class. Please, please, please come with questions, and we can definitely talk about this more. But for now, I'd like to go ahead and wrap up video 2.3, the supplementary video on separation of variables as they apply to drag problems. Go Bears.